Okay, so thank Nadia for the introduction, and it's very exciting to be here to share one of our recent work, efficient minimizer orders for large value of k using minimum decycling set. So I will start this talk with some basic definition like minimizer, universal heating set, and decycling set. So be a little bit patient about this part, and then I will tell you how can we combine minimizer order with decycling set and how is the performance. So given a sequence of length L is minimizer is the minimum k-mer in it, where the minimum is with respect to a predefined order. And in the right figure, I show an example for k equal to 4, L equal to 12, and we use lexicographic order to compare the order between k-mers. So for given a sequence in the bottom, we scan all the subsequence with length L from left to right, and for each subsequence with length L, we selected its minimizer in red color. So in totally we selected 3 k-mers as minimizer. And in minimizer scheme, we define the density as the ratio of k-mers selected as minimizer. So in this example, the density is 3 divided by 20. And the minimizer scheme has 2 very important features. First, you can see in this example, all the adjacent subsequences tend to share the same k-mer. Like the first 5 subsequences share the same k-mer. And the second important feature is identical subsequence with length L always selected the same k-mer as minimizer. It means for similar sequence, we always selected a similar set of minimizer. So based on these 2 important features, minimizer has a lot of application in metagenome classification, in bioinformatics tool development, like in metagenome classification, Kraken tool use minimizer to reduce the memory usage, and it also has many applications in other bioinformatics tools. So in practice, minimizer with lower density is preferred because it can help reduce the memory usage and the runtime more significantly. And the lexicographic order and the random order are 2 commonly used orders. And in 2019, Yaron and his collaborator proposed a new concept called universal heating set to further reduce the density. So given values of k and L, universal heating set is a set of k-mers such that every sequence with length and least L must contain at least 1 k-mer from the universal heating set. So given a universal heating set, we can define a minimizer order as follows. For k-mers within universal heating set are always smaller than k-mers outside it. And for k-mers within universal heating set, we use random order to compare them. In this way, we can get a minimizer order. And the minimizer scheme based on such an order will always select k-mer from universal heating set as minimizer because every L-long sequence contains at least 1 k-mer from the universal heating set. And note that the problem of searching for the minimum universal heating set is still open, and in their work, they proposed a heuristic algorithm thus to calculate a small universal heating set. And in their experiment, they show that minimizer based on the universal heating set calculated by DOS can generate lower density compared to minimizer based on lexicographic order or lower or random order. Like in the table here, in the human genome, a minimizer based on lexicographic order selected more than 500,000 k-mers as minimizer, while the minimizer based on the DOS algorithm only selected 150,000 k-mers as minimizer. However, even universal heating set-based minimizer order can generate low density, but currently is infeasible to calculate universal heating set for large k. So in the talk today, I will introduce minimizer order based on decycling set, which can provide low density similar to universal heating set or even lower than universal heating set, but it can easily scale to large value of k. So before I introduce our algorithm, I need to introduce 2 more concepts, doubling graph and the decycling set. I think most of the people here are familiar with doubling graph. So in doubling graph, each node is a k-mer, and there exists an edge from A to B if the surface of A is the same as the preface of B, like the subsequence I showed in red color in the figure. And in this way, we can also represent an edge by a k plus 1 mer by merging the overlapping subsequence between the two nodes. So a path of W nodes in the doubling graph represents a sequence of W overlapping k-mer. If we merging the overlapping subsequence between the k-mers, then every path will spelling out a sequence with length equal to W plus 1 minus 1, W plus k minus 1. And in a complete doubling graph, all possible k-mers are nodes and all possible k plus 1 mers are edges. And the decycling set is a set of nodes whose removal results in an acyclic graph. Then, in 1972, Michael Weiss proposed that the minimum decycling set contains exactly a single node from each pure cycle in the complete doubling graph. And a pure cycle is a set of nodes in the complete doubling graph corresponding to all cyclic rotation of some k-mer. Like here, I show the 4 nodes with yellow color show a pure cycle. And to decide which node in the pure cycle should be included in the minimum decycling set, he also proposed a k-mer embedding method. Given a k-mer, we define k roots of 1 in the complex plane, and then we put the k character in the k-mer on the complex plane in the counterclockwise order, like I show in the left figure. And then he used the formulation on the right to calculate a weight for each k-mer. In the formulation, the xi means the weight of the ith character in the k-mer, and the weight for letter ACGT is equal to 0, 1, 2, 3. So we finally can calculate a weight for this k-mer according to this formulation, and I show it by the black dot in the left figure inside the circle. Then given a k-mer, we can do 1 letter leftward rotation each time to get all the 5 cyclic rotation of this k-mer, and we calculated the k-mer embedding weight for all the 5 k-mer according to the formulation shown in the previous slides. And now we can define a k-mer as positive or negative according to the imaginary value of its weight is larger than 0 or smaller than 0. And if the weight is equal to 0, we call it as indeterminate. So the interesting point is Michael Weiss' paper proposed that we can select the first positive rotation k-mer to be included in the minimum decycling set for each pure cycle. And note that there also exists some pure cycle or all cyclic rotation of this k-mer may have weight 0. In this case, he proposed to select the lexicographically smallest one. So here is the minimum decycling set algorithm, and given the minimum decycling set, we can define a minimizer order as follows. For k-mers, willing minimum decycling set are always smaller than k-mers outside, and for k-mers willing it, we still use random order. But however, for large value of k, the size of the minimum decycling set increase exponentially with the value k, so it's too large to store it in memory, and also it will take too much time to search if a k-mer belongs to the minimum decycling set or not. So we propose an efficient algorithm to check if a k-mer belongs to the minimum decycling set or not without pre-computing and storing the minimum decycling set in memory in advance. So I will only show the intuition of our algorithm. Given a k-mer x, we use the k-mer embedding formulation to calculate its I-value. If A is negative, then A is impossible come from minimum decycling set. If A is positive, then we will do 1 letter rightward rotation of x to get the previous k-mer in the cyclic rotation, and check if the previous k-mer is positive or not. If A is non-positive, this k-mer will come from minimum decycling set, otherwise it cannot come from the minimum decycling set. And if the I value of x is equal to 0, then we need to check if all cyclic rotation of x have I value equal to 0. If yes, then we need to further check if x is the lexicographically smallest one or not to check if it comes from minimum decycling set or not. So before I show an example of our algorithm, I will show one more important lemma. In the doubling graph, for one node, all of its incoming neighbors will have the same I value. So according to the definition of the doubling graph, all of its incoming neighbors only differ in the first character, and according to the formulation to calculate the I value, we can see the weight of the first character is always multiplied by sin 0, and the sin 0 is equal to 0. So like I showed the formulation in the right, the red part is always equal to 0, and the other part is the same for all the incoming neighbors. So it's easier to get the conclusion. All the incoming neighbors have the same I value. So here is an example given a sequence on the left. Here we use parameter k equal to 5 and L equal to 8. Then we calculated the k-mer embedding value for all the k-mers in this sequence from left to right, and we indicated its I value is positive or not under the first starting letter of each k-mer. And note that for one positive k-mer that is alter a negative k-mer in this sequence, it must also alter a negative k-mer in the pure cycle containing the k-mer. So according to the lemma 1, so it must come from the minimum decycling set because it's the first positive rotation in the pure cycle. So in this way, it's easy to get the 5 positive k-mer that is just out a negative k-mer that come from the minimum decycling set. Now we can scanning the sequence from left to right for each window containing 4 overlapping k-mers. We will check how many k-mer from minimum decycling set it contains and check the minimizer in it. So for example, for the first window, there is only 1 k-mer from the minimum decycling set. We will select it as the minimizer. And for the second window, it contains 2 k-mer from the minimum decycling set. Then we will use a hash function to select the smaller one. And in this example, I use lexicographic order for simple. So we selected the second one. And in this way, we finally can select 7 k-mer from this sequence as minimizer. And here, all the arrows with red color means the minimizer is selected by hash function, either because the window contains more than 1 k-mer from the minimum decycling set, or because there is no k-mer from the minimum decycling set in that window. And to extend it, we also define a double decycling set based minimizer order. We first define a symmetric decycling set similar to the decycling set, but just instead of selected the first positive node, now we selected the first negative node. And then we define k-mers within the decycling set to be smaller than sequence k-mers within the symmetric decycling set, and they are smaller than the other k-mers. And for k-mers within each of the set, we use random order. So here is the result of our method. We compare our method with the random order and the universal heating set based order, and also minimization in expected density. And the expected density factor is calculated by calculating the average density factor for 10 random sequences. And here we can see the random order always have the worst performance, and the minimization performs better than random order, but worse than the universal heating set. And the universal heating set can only, for the universal heating set calculated by DOS algorithm, it can only calculate it for k up to 11. And for universal heating set calculated by Pasha, it can only be calculated up to k equal to 13. And our decycling set can achieve lower density factor than universal heating set, but it can also be easily scaled to large value of k. And here, in the right figure, I show another example for k equal to 11 and the L values from 1 to 20. We still can see that the performance between the methods are similar. the decycling set-based minimizer order always has the best performance, and when the value L is small, the double decycling set order has better performance, and when the L grows, the difference between the k-mers, between the methods becomes small, because when L grows, all the window contain multiple multiple k-mers from decycling set or from universal heating set. Then we use random order to compare k-mers between them. And here I show another example for large value k. When k equal to 20 is infeasible to calculated universal heating set. So we compare our method to random order and the minception. And the left figure shows the expected density on 10 random sequence, and the right figure shows the particular density for 10 random sequence subsampled from the human X chromosome, and the error bar shows the deviation between the 10 sequences. So we can see first the performance between the methods are still the same, but the random order and the minception has much higher deviation, and our decycling set-based order has lower deviation. And also, I think other performance is the same. When L is small, double decycling set has better performance than the decycling set. And we also show another example for large k. When k equal to 50 and 100, we have similar observation, but only two differences. One is when L is small, minception has better performance than the decycling set-based order, because when L is small, most of the L sequence didn't contain sequence come from decycling set, so we almost like use random order. And when L grows, then we can see decycling set still has the best performance. And another interesting point is here we also show the theoretical lower bound for the forward scheme, which is a class that is generalized sketching scheme that includes minimizer. So minimizer is a subclass of the forward scheme, and we can see the shape of decycling set-based order is very similar to the shape of the lower bound, but there is a constant gap between them. It's very interesting. We still didn't have theoretical result on it, but I think it's interesting to explore in the future. And here I show the runtime. We compare the runtime of decycling set-based order to other methods. When we know that random order always consumes less time, but as we know in the previous slides, it has the worst performance. And when k is big, compared to minception, decycling set and double decycling set based order consume similar time or even less time. And when k is small, if we compute the decycling set, pre-compute the decycling set and store it in the memory, then it consumes similar time compared to universal heating set based order. And if we calculated the membership on the fly, then it consumes a little bit more time compared to universal heating set, but less time than minception. So in conclusion, we introduce new minimizer orders based on minimum decycling set, which can guarantee lower density, but also can easily scale to large value of k. And in the future, we would like to extend it to sequence-specific sketching, or we try to realize the strict window guarantee of minimizer and see if we can get a better conservation. And also, in theory, the gap between the minimum decycling set-based order and the lower bound of the forward scheme is very interesting and deserves to explore. So finally, I would like to thank all my collaborators and thank all the supporting fundings. And our software is available on GitHub. And thank you all for your attention.